Welcome back to the channel. Today we will start with part 5 of Applied Physics 1, and we'll cover about laser. Let's get started. We'll be understanding these topics in our video today. A laser, light amplification by stimulated emission of radiation, is a device that emits light through a process of optical amplification based on the principle of stimulated emission of radiation. Lasers produce light that is highly coherent, meaning that the light waves are synchronized in phase and frequency. This coherence results in laser beams being very narrow, focused, and of a single color, monochromatic, making them unique compared to regular light sources. Key features of lasers are monochromatic light. Laser light is of a single wavelength or color, which allows it to interact precisely with materials and systems. Directional. Lasers emit light in a narrow, focused beam that can travel long distances without much spread. Coherent light. The waves of light emitted by lasers are in phase, meaning they have consistent timing and alignment. High intensity. Lasers can focus energy into a very small area, resulting in high intensity, which is why they are used in cutting, welding, and medical procedures. Coherence is one of the defining characteristics of laser light and is divided into two types: temporal coherence and spatial coherence. Temporal coherence refers to the consistency of the phase of the light waves over time. It measures how long the light waves remain in phase with each other. In simpler terms, temporal coherence describes how well the wave at one point in time correlates with itself after some time delay. Longer temporal coherence. The laser light waves stay in sync over a longer duration. This corresponds to lasers having a narrow spectral line width, very few wavelengths, which is why they are often referred to as monochromatic. High temporal coherence is important in applications like interferometry and holography, where light waves must remain synchronized over long periods to produce clear interference patterns. Spatial coherence refers to the consistency of the phase of the light waves across space. It describes how uniform the light wave front is over a distance perpendicular to the direction of propagation. High spatial coherence means that the light waves spread very little as they propagate. This results in a laser beam that is highly focused and narrow, allowing the beam to maintain its tight diameter over long distances. Lasers with high spatial coherence are capable of creating fine, sharp beams and are used in precision cutting, alignment, and optical communications. Diagram of temporal and spatial coherence would illustrate a laser beam showing consistent phase over time, temporal coherence, and a highly collimated, narrow beam, spatial coherence, in contrast to ordinary light, which spreads out and has inconsistent phases. The functioning of a laser is based on three key processes: absorption, spontaneous emission, and stimulated emission. The principle behind laser operation is stimulated emission, which allows for the amplification of light. Absorption. When an atom or molecule absorbs a photon light particle, an electron is excited to a higher energy level. The electron remains in this excited state for a short duration before returning to its original energy level. Spontaneous emission. After excitation, an atom can return to its lower energy state on its own by emitting a photon. This emission of light is random in direction and phase, which is how ordinary light sources like bulbs operate. Stimulated emission. Stimulated emission is the key to the working of lasers. When an atom is in an excited state and a photon of the correct energy interacts with it, the atom is stimulated to drop back to a lower energy state. Basic components of a laser are active medium or gain medium. This is the material in which the laser action takes place. The active medium can be solid, liquid, or gas. Energy pumping or excitation source. The atoms in the active medium need to be excited to higher energy levels. This is done using an external energy source, known as a pump source. Optical resonator or cavity. The optical cavity consists of two mirrors placed around the gain medium. One of the mirrors is fully reflective, while the other is partially reflective. Output coupler. The partially reflective mirror or output coupler allows a portion of the amplified coherent light to escape the cavity as the laser beam. Process of laser action includes pumping, population inversion, stimulated emission, amplification, and laser output. You can look at them in this slide. Diagram of a basic laser system shows the active medium, the pump source, two mirrors, one fully reflective and one partially reflective, and the output beam. It would also illustrate the process of stimulated emission and the resulting amplified light within the optical resonator. The theory of laser operation is rooted in the work of Albert Einstein, who introduced the concept of stimulated emission in 1917. He derived the relationships between the processes of absorption, spontaneous emission, and stimulated emission using a set of coefficients, known as Einstein's coefficients. These coefficients describe how atoms interact with radiation and help explain the process behind laser action. There are three key processes associated with the interaction between matter and radiation, each of which is described by an Einstein coefficient. Absorption B12. When an atom absorbs a photon, it is excited from a lower energy state, E1, to a higher energy state, E2. This process is described by the Einstein coefficient B12. The rate of absorption depends on the number of atoms in the lower energy state and the radiation density at the photon's energy. Spontaneous emission A21. When an excited atom spontaneously returns to a lower energy state, E1, it emits a photon in a random direction. This process is described by the Einstein coefficient A21. The rate of spontaneous emission depends on the number of atoms in the excited state, E2. Stimulated emission, B21. If a photon of energy equal to the difference between two energy states interacts with an excited atom, it can stimulate the atom to emit a photon identical to the incoming photon. This process is described by the Einstein coefficient B21. The emitted photon has the same phase, direction, and energy as the incoming photon, leading to coherent amplification of light. Einstein's coefficients are related to each other, and their ratio helps understand the probabilities of these different processes. The balance between absorption, spontaneous emission, and stimulated emission is key to achieving population inversion and, therefore, laser action. The helium-neon laser is one of the most common and widely used types of gas lasers. It was the first continuous wave laser developed and is known for emitting red light at a wavelength of 632.8 nanometers. Construction. Active medium. A mixture of helium and neon gases is used, typically in a ratio of 10:1, helium to neon. Energy pumping. Electrical discharge is used as the pumping method. The high-voltage discharge excites the helium atoms, which then transfer energy to the neon atoms through collisional energy transfer. Optical cavity. The laser consists of a long, narrow tube with two mirrors at the ends. One mirror is fully reflective and the other is partially reflective, allowing laser light to escape. Working principle for helium-neon laser is excitation. Helium atoms are excited to higher energy levels by electrical discharge. Energy transfer. The excited helium atoms collide with neon atoms, transferring their energy to neon atoms. This process excites neon atoms to higher energy levels. Stimulated emission. When neon atoms drop to lower energy states, they emit photons of light. These photons stimulate further emission of identical photons from other excited neon atoms. Laser output. The coherent photons are reflected between the mirrors, amplifying the light. A portion of this light escapes through the partially reflective mirror, producing the laser beam. Characteristics of helium neon laser are: wavelength is 632.8 nanometers for red light. Output is typically continuous wave mode. Low power, making it safe for many applications. Applications of helium neon laser are optical alignment, holography, barcode scanners, and interferometry. A diagram of the HENA laser shows a glass tube containing the helium neon gas mixture, electrodes for electrical discharge, and mirrors at each end to form the optical cavity. The diagram would illustrate how helium atoms transfer energy to neon atoms and the emission of coherent light. The Ruby laser was the first laser ever built, developed by Theodore Maiman in 1960. It is a solid-state laser that uses a synthetic ruby crystal as the gain medium. The laser emits red light with a wavelength of 694.3 nanometers. Construction of Ruby laser includes active medium. The gain medium is a ruby rod made of aluminum oxide with chromium impurities. The chromium ions in the ruby are responsible for the laser action, as they absorb light and re-emit it at a specific wavelength. Energy pumping. A flash lamp is used to pump energy into the ruby crystal. The intense burst of light from the flash lamp excites the chromium ions to higher energy states. Optical cavity. The ruby rod is placed between two mirrors, forming the laser cavity. One mirror is fully reflective, and the other is partially reflective to allow laser light to escape. Working principle includes excitation, spontaneous emission, stimulated emission, and laser output. Characteristics of ruby laser are: wavelength is 694.3 nanometers. For red light, output is typically pulse mode. Ruby lasers can deliver high-energy pulses. Applications of ruby laser are in holography, tattoo removal, laser rangefinders, and material processing. Diagram of the ruby laser shows a cylindrical ruby rod placed between two mirrors, with a flash lamp wrapped around the rod for optical pumping. The diagram would illustrate the excitation of chromium ions and the generation of a red laser beam through stimulated emission. Lasers have found applications in many fields due to their unique properties, such as coherence, monochromaticity, and high intensity. Some of the key laser applications are in medical applications for laser surgery, dermatology, and dental procedures, industrial applications for cutting and welding and material processing, in fiber optic communication, military applications for laser rangefinders and laser targeting, scientific applications in holography and interferometry, entertainment and display in laser shows and barcode scanners, in metrology for precision measurement. Quick summary. Lasers are special sources of light that emit highly coherent, monochromatic, and intense beams of light. They are widely used in fields like medicine, communications, and industry. Temporal coherence refers to the consistency of phase over time, indicating how well the light waves maintain their frequency and phase over a period. It allows lasers to be monochromatic and useful for precision applications. Spatial coherence describes the uniformity of phase across the light beam, allowing lasers to produce narrow, focused beams that can travel long distances. The principle of lasers is based on stimulated emission, where photons of the same phase and frequency are emitted, leading to the amplification of light within an optical cavity, producing a highly focused and coherent beam. That's it for today's video. We will look at other topics in our next video. Till then, please like, share, and subscribe to the channel. See you in the next video.